In section 8.1, we start to look at arc length. Now, when you look at arc length, you have to think about what does that mean. If you were to take string, if you were to take this figure 1 right here on the left and put string against it, you could stretch the string out and measure it using a ruler. But to measure the length of that curve is not something we've worked with before. We kind of did in chapter 4 in polars, so it feels a little backwards. But if you were to use polygons, you can estimate, and the smaller your side lengths get, the better your approximation is. So as you can see over here, if we were to take a continuous curve and divide it into pieces, we can get a polygonal approximation and we can add that up. So what this is leaning in towards is that we can use calculus to find the length of a formula because we can use the antiderivative. So the arc length formula says that if f prime is continuous on a closed interval from a to b, then the length, or an inclusive interval from a to b, then the length of the curve y equals f of x from a to b is given as L equals the integral from a to b, the square root of 1 plus f prime of x quantity squared dx. Leibniz notation is the one that's most commonly used here. That's the one we're going to use. So when you have a y, you take the derivative of it, square it, add 1, put it in a square root, and find the length from a to b. Sounds simple. We know it looks believingly simple. So let's look at a couple examples of using this. This problem says find the exact length of the curve. So it says 36y squared equals x squared minus 4 to the third power, and x is between 2 and 3, and y is greater than 0. So we need to solve for y first, because we need dy over dx. So I'm going to say y squared is 1 over 36, x squared minus 4 to the third. So y equals plus or minus the square root of 1 over 36 times x squared minus 4 to the third, which if you think about it, it's plus or minus 1 over 6 times the square root of x squared minus 4 to the third. So y equals plus or minus 1/6 x squared minus 4 to the 3/2. Now, one of our conditions up here is that y is greater than 0, so we can lose the plus and minus and just say 1/6 x squared minus 4 to the 3/2. Now, in order to find arc length, we're going to use the formula we just talked about, and it says the integration from a to b of the square root of 1 plus dy over dx, quantity squared with respect to x. So we need y prime. Here we have y. Let's find y prime. So we keep the 1/6, and the derivative of x squared minus 4 to the 3/2 is chain rule. So we have 3/2 x squared minus 4. And when we take away 1, we have a half here, times the derivative of the inside is 2x. So let's simplify that a little bit. The 2's cancel. 3 and 6 reduce to 1/2. So we say 1/2 x times x squared minus 4 to the 1/2. So that's our dy over dx. That's the same notation. You can write it either way. So we have the integration from a to b in terms of x, means we go from 2 to 3. And we have the square root of 1 plus 1/2 x. We have a bracket here. 1/2 x, parentheses x squared minus 4 to the 1/2 quantity squared with respect to x. So this means we have the integral from 2 to 3. The square root of 1 plus, now that's all one term, so 1/2 squared is 1/4, and then we have x squared, and when we square that square root, we just have x squared minus 4 dx. Think about the fact that this is all one term, so you can square it piece by piece. So L equals the integration from 2 to 3, the square root of 1 plus 1/4 x to the 4th minus 1/4 of 4 is 1, so we have x squared dx. Now this would be nice if it simplified nicely, so let's try it. We have 1/4 x to the 4th minus x squared plus 1 dx. So can that simplify? I think if you got a common denominator for all of this, you would see it a little more easily. So let's do that. Common denominator of 4. So this numerator is x to the 4th minus 4x squared plus 4 dx. Well, then we could factor the 1/4 out. So we have 1/4 parentheses x to the 4th minus 4x squared plus 4 dx. Now the square root of 1/4, because it's factored out, we could take the square root of 1/4 to be 1/2. And then in the square root, this factors into x minus x squared minus 2 quantity squared. So that means our square root's going to go away very nicely. So the square root of a squared is gone, so we have x squared minus 2 dx. Now, that's often your goal, is to see if you can factor it in some way for the square root to go away, unless it's trigonometry. So it makes for an interesting problem. So now that we've simplified it, let's bring this 1/2 out front. And you can see that we really have simplified it, and this is a very simple integration. So we have 1/2 parentheses. The integration of x squared is 1/3 x to the 3rd minus 2x from 2 to 3. So we have 1/2 times, when we put in 3, 27 divided by 3 is 9 minus 6 minus 1/2. And when we put in 2, we have 8/3 minus 4. So we have 1/2 of 3, which is 3/2. Let's go ahead and write it that way. Minus, this would be 8/3 minus 12/3. So we have minus 1/2 times negative 4/3. So we have 3/2 minus, or plus, that would be 4/6, which reduces to 2/3. So your common denominators are 6. So this would be 9, and 2 times 2 is 4. So the final answer is 13/6. So that's the length of that arc from 2 to 3 when y is positive. So that's the exact length of the curve. Now, the reason this is helpful is your most famous example is the curve in the St. Louis Arch. And as you can see, as stated below, the Gateway Arch in St. Louis, Missouri was completed in 1965, and it was designed using an equation with a hyperbolic cosine function. So that's just really interesting to see and to use. So the length of the arc is not that hard. You have to keep manipulating your equation until it works. Now, if your curve has the equation x equals a function in terms of y, then this is going to be switched. Notice that here, instead of dy over dx, we have dx over dy, and we're in terms of y, and the bounds are in terms of y, because up above it says that y is in between c and d. So if you have a continuous, you just switch it up accordingly. So let's look at one of those. The problem here says x equals 1/3 times the square root of y times y minus 3. and y is between 1 and 9. Now, as you can see, that's not something we solve for y equals. So we're going to figure our arc length in terms of x. So we're going to say L equals the integration from 1 to 9. We have the square root of 1 plus. Now here we're going to have dx over dy. So the derivative of x in terms of y squared, and our bounds are going to be y. So let's take that x equals 1/3 times the square root of y. Let's call that y to the 1/2 times y minus 3. So we can distribute. So we have 1/3 y to the 3/2 minus 1/3 of 3 is 1, y to the 1/2. So now let's find the derivative of x, which is the same thing as dx over dy. The derivative of this function x in terms of y. So that's x prime, not x to the first, equals 1/3 times 3/2. Y to the 3/2 minus 1 is 1/2. Minus 1/2 y to the minus 1/2. So we can put that over here and say L equals the integration from 1 to 9, the square root of 1 plus, now our derivative is, these 3's cancel. So we have 1/2 y squared, y to the 1/2 minus 1/2 y to the minus 1/2 quantity squared with respect to y. So we need to multiply those out and do FOIL. So we have the integration from 1 to 9, the square root of 1 plus 1/2 times 1/2 is 1/4, y to the first, minus, if you multiply those, you have 1/4 and doubled is 1/2. And when you multiply the y's, you add the exponents, and so it becomes y to the 0, which is the number 1, plus 1/4 y to the minus 1 with respect to y. Now pay attention to that and pay attention to what happens next. We're going to add these like terms, and we're going to say, before we do, notice that this is what happens when you squared that stuff above. And now we're going to add these like terms. So L is the integration from 1 to 9, the square root of 1/4 y plus 1/2, 1 minus 1/2 is plus 1/2, plus 1/4 y to the minus 1 dy. Now what's really great here is I know that this factors because I did FOIL to get the stuff with the gray underline, so now I can factor it to look exactly the same. So we're going to say the square root of 1/2 y to the 1/2, not exactly the same. This is a plus because the 1/2 changed from a negative 1/2 to a positive 1/2, plus 1/2 y to the minus 1/2 quantity squared dy. Now this is beautiful because whenever you see a squared and a square root and everything inside is squared and you're in a square root, all of that cancels out. So now we have L equals the integration from 1 to 9. The square root is gone. So we have 1/2 y to the 1/2 plus 1/2 y to the minus 1/2 with respect to y. So we can integrate normal integration. We're going to say L equals, we have 1/2. When we add 1 to the 1/2, we get 3/2, and the coefficient is 2/3, plus 1/2. When we add 1, we get y to the 1/2, and when you divide by 1/2, it's like multiplying by 2 from 1 to 9. So this means we have 1/3 y to the 3/2 plus the 1/2 of 2 is 1, y to the 1/2 from 1 to 9. So let's plug in the 9, and we get 1/3 times 9 to the 3/2 plus 1/3 times 9, the square root of 9. That's what the y to the 1/2 means. Minus 1/3 times 1 to any power plus 1 to any power. Now, this 9 to the 3 halves, I'm going to bring down my 1/3 real quick. This 9 to the 3 halves means the square root of 9, which is 3, cubed is 27, plus 1/3 times 3, minus 1/3 plus 1 is 4/3. So 1/3 of 27 is 9, plus 1, minus 4/3. Common denominators is 27 over 3, plus 3 over 3, minus 4 over 3, makes 26 over 3. So that is the exact length of the arc. And notice why we did everything in terms of y. It's because our function is a function of y, a function of x in terms of y, instead of a function of y in terms of x. So I think that covers all that you need to do the problems that you have in your exercises, and hopefully you're good with that. If you have any questions, let me know. Thanks.